Hello everyone, this is Jim Corkins again, and we are moving on to projectile motion, and specifically we're going to be dealing with just projectiles that are shot horizontal to the ground with no launch angle at a height off the ground. Okay? If you haven't done the reading, please go to Coletta chapters 1, 2, and 3, OpenStax chapter 2 and 3 if you're in Physics 111, and OpenStax 2, 3, and 4 if you're in Physics 121, and start on your sapling homework. So to review, what we've done is we've done some we've done kinematics in 2 dimensions, and now we've done relative motion, and now we're doing projectile motion. So with projectile motion now, instead of the regular acceleration of A, we're going to have an acceleration of G, okay, in the Y direction. And in the X direction, you can have an acceleration in the X direction, but with projectiles in a situation where there is no air, a free fall situation like we studied earlier, where there is no air, everything falls at G. And so in the X direction, you're going to have a constant velocity. There's going to be no drag force slowing down the projectile as it's moving in the X direction, or in the Y direction for that matter. So, but the gravity, things are going to be falling at free fall, which means gravity. I'm going to mark up this document here. I hit the comments button, close it, and now I have a little pencil. And again, just to remind you that G is 9.8 meters per second squared. And the vector for it is going to be down. So that's why we have a negative in front. G isn't negative necessarily. You could switch your coordinate system and make down positive if you want, but most of the time we're going to consider down as negative. And so that's why we have a negative in front. But the magnitude of that acceleration is 9.8 meters per second squared. Okay? So when we do a linear fit, when we do a curve fit in a Y versus T graph, and so this is a Y versus T graph, this is going to be the fit for that. Okay? And then in the velocity versus time, so it would be V sub Y versus T, we're going to have a linear fit for that of this graph. In the X direction, since motion is going to be constant for projectiles, it'll be a linear fit, and there would be no point in doing a velocity in the X direction versus time fit, because it's just if stuff is moving at a constant velocity, the initial velocity is equal to the final velocity. Okay, so these are going to be the 3 things that we're going to be using for all of projectile motion. Okay? Well, let's get to it. Suppose you're given a problem like this. A bullet is fired from a gun at 200 miles an hour. I mean, just think of how fast that is. Okay? And another bullet, identical bullet, is dropped from the same height. And as the moment that this bullet leaves the barrel, you drop this other bullet with no initial velocity, and you let them both go. Which one is going to hit the ground first? Is it going to be the dropped bullet, the fired bullet, or the same time? And I want you to also explain your reasoning too. So think about the reason why you think things are the way they are. Okay? Was there an experience, or do you think there's something driving it, like an impetus force or something like that? So please pause the video, answer this question, and it's a very important question. And also, once you answer it, try to explain, really think to yourself why you believe that. Why do you think that is the way it is? All right? Is it experience, or do you think there's a theory driving it? Okay, so what are your reasonings for that kind of thing? There's always got to be a logic to it. Pause the video now. Well, let's try to answer that question. We'll come back to this, and let's try to answer that question, and let's only look at objects that are shot horizontally. Okay. So if you shoot a ball horizontally, okay, again, these are all the projectile motion problems that we're going to be doing. So I just want to, well, we're going to be dealing in this first part with projectiles just shot horizontally. Okay, so hopefully in answering that, when we get finished doing some problems and turning this type of motion over in our heads, we'll be able to come back and we'll revisit this problem and try to answer it. Okay, so to remind you, here's going to be the model that we're going to be using. So we're going to try to make some assumptions as to objects in the free fall. So we're going to be ignoring air resistance. Okay, some problems, not in our class, when you get in higher levels, you can't ignore air resistance, so you have to take that into account. And it's called the drag force, and it's based on the surface area relative to the motion of the air. And there's things that you could do. So it's a little bit more complex of a problem, but we're going to just consider free fall situations. Okay, then you're going to do a pictorial representation, and you're going to actually draw. So this is how we're going to approach these problems. You're going to actually draw the projectile as it's moving in the Y and X direction. Okay, so if it's a ball, it would probably be doing this, and then this, and then this, and then finally. So anyways, so it would probably be doing that kind of motion, right? If it's being shot horizontally. All right, and then what you're going to do is you're going to, acceleration in the Y direction is going to always be G, so it'll be G down. And then what we're going to do is list off our kinematics equations that we're going to be using, and then we're going to list off what our knowns and unknowns are. And then we're going to go ahead and try to find time. In all of these problems, the thing that links motion in the X direction to motion in the Y direction is time. That's the only thing they have in common. The time it takes for this ball shot horizontally to travel and then hit the ground over here is it's going to be the time it takes to travel horizontally is the same time it's going to take for it to travel vertically. Okay? So that's going to be the approach. We're going to try to draw a picture, if it's not already given it to us. Then we're going to list off our known and unknowns, and then we're going to list off our kinematics equations and alter them to fit the situation. And then we're going to try to solve for time to link the two, the X direction motion and the Y direction motion equations together, and try to solve for what we're doing. Then what we're going to do is check out our problem to see if that makes sense, right? And so we're going to assess it to see if the answer is reasonable. Okay? So with problems, typically with zero launch angle problems, you have something on a cliff and it's being launched straight out at a zero launch angle. That's what it means, 0 to the horizontal launch angle. So all of the objects' initial velocity, in this case a diver, all of their initial velocity is going to be in one direction. You know, obviously down here, now that initial velocity is now a final velocity as it's right before it's impacting the ground. We're not considering velocity after it's hit the ground, because that's not a part of the projectile motion. That would be a part of the impact, right? Which is momentum stuff. We want to consider just the velocity right before it hits the ground as the final velocity, okay? So that would be the velocity, and it would have two components. It would have an X direction component, and it would also have a Y direction component. And the Y direction component would be down. Also, you're going to have to know that the acceleration vector is always going to be down, and it'll be at G. So that acceleration vector is going to be down at G. And that height, typically, I like to consider the initial up here, and the final is going to be a negative final down here. So this is going to actually, typically the delta y is going to be negative, and so that's going to be actually a height below your initial point, right? And it kind of helps with the math. If you consider the fact that wherever the person starts at, that's going to be y is equal to 0. And now they're falling below their initial position, so you're going to have a negative height, which sounds weird. You have a negative height. Usually we consider ground as a height, but really if they're I like the math that works out easier. So what is happening? So let's show this. So you've got a person who's going to be taking this path right here. And so in the first second, so this is 0 seconds is their start, is right here. Okay. And then here's the 1 second mark, and here's the 2 second mark, here's the 3 second mark, here's the 4 second mark, here's the 5 second mark, here's the 6 second mark, and here's the 7 second mark. Now, in the first second, they're traveling this direction. In the second, they're traveling in this direction. In the third second, here's the velocity. So I'm just drawing arrows for their overall velocities in between each second, right? And we've done this before. We did this before in the tutorial earlier with accelerated motion. But now we have to consider this. Now, if you think about it, this vector is kind of slightly pointed down, correct? So in the x direction, it traveled this distance in the x direction. So in the first, it traveled 1 meter. Okay, so at this point right here in the x direction, they're down here. And in the next second, it traveled another vector here. And in the third second, it traveled here. In the fourth second, it traveled there. 5th second, 6th second, from the 6th, 7th. So it looks like at each point in time, it looks like it's traveling at about, in between each point in time, at about a positive 1 meter per second, right? So if each one of these is 1 meter to the right, this looks like it's traveling at a positive 1 meter per second at a constant velocity like that, okay? And this is common for free fall situations. Typically you have no acceleration in the x direction. It's not common. It is free fall for a projectile. Now in the y direction, it's a little bit more complicated, right? So just to revisit, I'm sorry, real quick. In the x direction, it looks like their velocity is going to be positive 1 meter per second, and it's a constant velocity. In the y direction now, again, it's a little bit more complicated. Okay, it looks like they're trailing just a little bit down. So in the y direction, they're right here at this point, and then right here at this point, and then right here, maybe right there, and then right just above the 6 mark. I'm trying to be consistent. It looks like they're in about the mid part of that. Okay, and then finally right here. So that y direction vector is getting longer over time, right? So that's the y direction vector. It's getting much longer over time, and it's best to look like this. The arrow is really small in the beginning, and then it's getting longer and longer and longer over time until it's really long. So that looks like it's speeding up in the y direction, right? So if it's speeding up in the y direction, that means something is velocity vector is increasing in the y direction. So what that tells me is that if it's constant velocity in the x direction and it's speeding up in the y direction, that means there's an acceleration vector which is only pointed down. And I'm going to use pink for that acceleration vector. And that the difference between the length in the first, from the 2 to 1 second, and from the 1 to 0 second, that difference in that vector looks like it's about that big. If I add that red one to this one, it should be equal to this. So it looks like this acceleration vector, which is really small. I apologize for this being really small. I'll try to thicken it so you can make it out. But it looks like it's just a little bit of an arrow. And at each one of those points, this y direction gets added to this, and now that's this vector right here. Add this vector here with that acceleration vector, and that's the next part. Add that next part to the acceleration vector, and that's the next part, right? So that's what acceleration is doing. It's just adding a velocity vector for every second that the object is falling, right? And so we know the length of that. We know the length of that. That's 9.8 meters per second. It's adding a 9.8 meters per second for every second, okay, in the downward direction. So that's that acceleration vector. So you could see here that this object has got a constant velocity in the x direction, and it's speeding up in the y direction, okay? And all of its initial velocity is only in the x direction, and it looks like it's starting from rest in the y direction, okay? So this is basically that situation, again, just this person's throwing a ball, but it's the same type of situation, okay? So with this type of motion, with this type of projectile motion, if you have a ball that is basically a ball that is shot horizontally, well, it starts with an initial velocity only in the x direction, and it has no initial velocity in the y direction. Okay, and so after the next second, now it has a velocity in the y direction, but it's still got that initial velocity in the x direction that is constant. So suffice it to say, here's the situation. If you shoot a ball straight out and you drop a ball, they're both starting with, both the shot ball and the dropped ball are starting with an initial velocity in the y direction of 0. And since the x direction motion is not affecting the y direction motion at all, in fact the x direction motion is constant for the shot ball, that is not affecting the y direction motion at all. The only thing affecting the y direction motion at all is this acceleration due to gravity. So since both objects are starting from rest in the y direction, and gravity is acting on both the objects, what happens with a dropped ball and a shot ball is that they are directly across from each other the entire time that they're dropping. They are directly, so if you look at this, each one of these balls, this is the drop ball, this is the shot ball, they are right next to each other the entire time that they're dropping. And what you find out is, even though this guy is shot, this ball is being shot in the x direction, they end up hitting the ground at the same time. Okay? And so back up here, you would say both of these hit the ground at the same time. Okay? Because we are seeing that right here. Okay? And so in the x direction, its velocity is constant. So it's got a constant velocity. Since it's got a constant velocity, that it doesn't have a positive 1/2 axt squared. That is 0. So this doesn't exist. Okay? So this whole part doesn't exist. There is no acceleration in the x direction for this ball right here. It's got a constant velocity, so that curvilinear portion of an x versus t graph doesn't exist. It's constant velocity. Well, in the y direction, in our case of the dropped ball, it has no initial y direction velocity. And since it's landing below, its final position is below its initial position, it's got initial position of 0 as well. So it's dropping below, and that is its height below where it started out at. And then it's going to be accelerating down at 9.8 meters per second squared, right? And so its final velocity should be directed straight downwards, so that final velocity vector in the y direction is a negative, right? So this is the final velocity, v final y, which is negative. And its v initial y is equal to 0. and it's v initial x, in this case, is v initial x is equal to its v final x, which is equal to positive 1 meters per second. And I got that because it's traveling 1 meter in from the 0 to 1 second, and it's doing that every time. Okay? So there's some really cool assumptions that we could make. In fact, it's delta y, it's going to be dropping below, most likely. We're going to be considering it's going to be dropping below its initial position. And its final velocity is going to be in the negative direction, but it's going to have a constant velocity in the x direction. So its displacement to the right or to the left is going to be at a constant velocity. So here's the conclusions or assumptions that we can make for an object launched straight horizontally at a 0 launch angle. Theta is going to be equal to 0 when it's launched horizontally from a height in the air. Okay? So there's a bunch of cool problems that we could do. Okay? And all of these are the typical types of problems that we're going to do. Okay? Oh, I forgot to say one thing here. The first thing you need to do in both of these cases is find delta t, the time of flight, right? Because the time it takes for it to fall this distance of basically 9.5 meters, right? 9.5 meters to the ground is the same time it's going to take for it to travel 7 meters to the right. So you need the only link between the y direction motion and the x direction motion is time. So it's vital that you get time first so you can link. So whatever you're solving for, whatever they're asking for, this first problem is how far off the base of the building does the ball hit the ground. Well, if we need to find that would be a delta x, well, if we're given a launch angle, we don't know delta t. We're going to have to find delta t from the y direction equation. So let's do this first problem, shall we? Okay, what I'm going to do, I'm going to show you how to work in groups together. So if you're ever given a problem and you want to work with your friends in groups, one of the best tools that we have is this whiteboard problem, this whiteboard. So I'm going to drag this down just a squidge. Okay, so here's my whiteboard thing. What I'm going to do is I'm going to take a snip, and to find snip on your computer, just type SNIP, and it'll bring up the snip tool. I use it so much, I just put it on my taskbar. Okay, so I'm going to snip this guy, and when you do that, it brings up this right here. So you hit New, and it allows you to screen capture. And now I'm going to highlight a screen capture of a problem right here, and we're going to do this problem together. Okay. And so how I would do it is I'm going to use this. It's Microsoft Whiteboard. And if you go to the Microsoft App Store, it's a free app. You just type in Microsoft Whiteboard, or you could go to the resources area, and I have a link for it. Okay. So this whiteboard, you have to create an account, a Microsoft account. It's free to create. And if you have a created account, all right, you can see I've done a lot of whiteboarding. You create a new whiteboard, this pops up, and now that snip, you could Control Z. What just happened? Let me hold on. So in the settings here, you could set your background, and I don't like really fine dots right there, so I'm going to format my background, and I want to choose these big. I like the hybrid one, so that makes these blocks big blocks. Okay. Let me drag this down a squidge. Actually, let me pause it, and I'm going to go ahead and increase the size. So I'm going to increase the size of this recording. Okay, so I have my snip up, so I'm going to copy this, and I'm going to just Control V and placed it someplace. And when you do it, typically it pastes it really small. Okay. Now, if I had any friends on that I want to invite to this, you just click up here where the little person is, and you hit the plus button, and you create a web sharing link. And if you're doing Zoom, like Zoom or WebEx, you could copy this link and then paste it into the Zoom wherever the Zoom IM that you have a little texting area on the right hand side of Zoom, and you could paste the link right in there. And when people click on it, if they have a Microsoft account and they also have a whiteboard installed, they'll be able to see this, right? So they'll be able to jump in and they could actually draw. Now, one setting that I don't like is where it's active pen. If you do that, the pen is on all the time. I like to keep that off, right? I like to keep ink to shape, ink to table, object snapping, okay? And so if this active pen is on, you can't move this, or you can't, it's hard to switch between moving this. You can't move it around. Whatever your pen is set at, you can't move it around. So take your pen off, and that means you could move this around, and then you click on the pen icon and you could draw, right? You could also erase, and I think you could even erase, well, you can't erase on any objects that you copy in, but you could use different pens, sparkly pens. You could use a highlighter. You could grab stuff. You could grab sections. So if you draw something like this and you want to grab it, highlight it, and you can move it over. So there's a lot of cool tools. It's best to just goof around with it. Incidentally, for the pens, I like this setting for the thickness of the ink. This setting is a little too fine, right? So it's best, if you're going to communicate with other people, right there, that you use this mid-setting pen. The other thing that's really cool about this is, as you saw before, it shows. So if you use this whiteboard before, it will save whatever whiteboards that you have onto your whiteboard. Okay, so you could come back to this, and you could even send people links to old whiteboards that you've done so they could check out what you've done, right? Anyways, so let's do this problem, all right? And we're going to try to follow the format that right here. Okay, so what the first thing that we're going to do is kind of model what is happening in this problem. Okay, I'm going to go to my whiteboard and I'm going to draw an X versus T graph. X versus T graph, and this is Y direction, and it says it's 13 meters high. So 1, 2, 3, 4, 5, 6, and 13. So each one of these tick marks is 1 meter. Can't believe I got that lucky with this. So I'm just going to move this Y. You know what? I should just have erased that. And I'm going to erase this too. Just use the eraser then. So I want to label this stuff right here. Okay, so we know it's 13 meters high. Okay, and it's going to be falling down to 0 meters, right? Actually, that would be, this is 0 meters down here. Okay, so a ball is going to be thrown horizontally at a speed of 9 meters per second. Okay, so we're going to say this has got a huge initial velocity. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So the length of its initial velocity vector in our blocks, by the way, is going to be, if each block is, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 meters, okay? 13 meters. If each block is 13 meters, its first vector is 9 meters per second, okay? So its initial velocity is 9 meters per second in the first second, okay? And the thing about gravity is going to be pulling it down at roughly 10 meters per second. So what is that? So within its first, so it's going to be pulled down at negative 9.8 meters per second squared. So the acceleration vector is going to be working on this at negative 9.8 meters per second, right? Well, we could see from that, okay, that it's probably only going to take about, maybe one to 2 seconds to hit the ground, probably. So if we get a delta t that is greater than 2 seconds, then there's probably a mistake. I'm estimating delta t to be 1 to 2 seconds, and I'm thinking it's not going to get, it's not going to, if it's going to have a constant velocity, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to be over here at this point. So this is adding negative 9.8 meters per second to this first second, right? So I'm thinking that it's going to be maybe, it's not going to take much for it to hit the ground, right? So let's list out what we're given, right? So it's going to fall 13 meters. So I'm going to use, for y direction stuff, I'm going to use blue, okay? And I'm going to consider t as the median, okay? So I'm kind of trying to list out what is going to be happening here. So let's go ahead and do this. I'm going to write what we're given. It's got a delta y. It's going to be falling 13 meters below its initial position. And in fact, I'm going to restructure this. So it's going to start off up here at 0 meters. And then it's going to be falling down 1 meter, 2 meter, 3 meter, 4 meter, all the way to negative 13 meters. And I'm going to consider this the 0 meters in the x direction, and we need to find its distance. It's probably going to hit the ground over here somewhere. Its final position, basically it's delta x in the x direction, right? The initial, if this is the initial position, then its final position here, x final, is the delta x, right? And so delta y, in the y direction, this is the y final position. If the y initial position is 0, then delta y is going to be that negative 13 meters. Okay, so delta y is negative 13 meters. It's going to have an acceleration in the y direction of negative 9.8 meters per second squared. Okay, so I'm going to put negatives in front of that too to keep me honest when I'm making my equations. All right. In the x direction, I'm going to use red. It's given, and so we need to find the delta x. So we're finding delta x in the x direction, which is actually x final. We're trying to find out how far it went. If x initial is going to be 0 meters, it starts off at 0 meters, then we need to find out what that is in the x direction. Okay, but what we are given is that the initial velocity in the x direction is a positive. It's to the right at positive 9 meters per second. And we're also given that it starts from rest. If it's only shot straight out, then its initial velocity in the y direction is going to be 0 meters per second. Okay? So both of these, we don't know what the time of flight is. So we need to find the time of flight. That's going to be important. And so, and the reason why I'm saying this is we need to find, we're trying to find how far it traveled in the x direction. And here's our x direction equation, right? We know the initial velocity in the x direction, but we don't know delta t. In order to find that, we're going to actually have to do some curvilinear stuff. So the motion in the y direction, right, is going to be delta y is equal to VIY delta t minus 1/2 gt, and that should be delta t squared. Okay, but the velocity in the y direction, the initial velocity in the y direction is 0, right? So we're going to be using this equation to find delta t. So we're going to be finding what delta t is here. Okay, we're going to be finding delta t and then using that to solve for this. Okay, so let's go ahead and do it. I'm going to we need to isolate delta t here, so I'm going to multiply both sides by -2 and divide both sides by -g, and so that'll be 2 divided by g. This is actually, if I rewrite this, this is actually just g divided by 2, right? It's actually -g divided by 2. And that's negative delta y, right? And that's equal to delta t squared, right? Well, the negatives will cancel out, and then what we'll get here for delta t squared, I'm going to square root both sides, is we're going to get 2 delta y over g square root. Okay? And so, since this thing is falling 13 meters below its initial position, right? Okay, and I already put the a negative in the equation, so it's falling 13 meters below its initial position, right? So you're going to get a square root of 2, and this is 13 meters below its initial position. The negative was taken care of by right here. I don't know why I started plussing things. I apologize. I put the negative in the equation from the beginning, so that got rid of this negative 13. Negative delta y equals negative 13, so that's just 13. And g is, the negative in the g is already taken care of, so we're actually just solving for magnitudes at this point. So this is 9.8 meters per second squared. And so delta t is going to be equal to the square root of all that. Well, that is 26 divided by 9.8. I'm going to get out my calculator. 20. Come on. 20. Is there a problem here? 26 divided by 9.8. And then we're going to square root that. 1.62. Actually 1.63. So our delta t is going to be 1.63 seconds, which kind of makes sense because we are estimating it to be somewhere in between 1 and 2 seconds, right? 0 seconds to 1 second. So we're pretty accurate in our guess, our estimation of that, right? So now we're going to take this time that it's going to take. This is the time it takes for it to just fall straight down. Okay. That will also be the time it takes for it to move that x direction right over here. Okay, so I'm going to take this equation right here. And I'm going to just move it over a little bit so it's nice and clean. We're going to plug that VIX in here. And so to get delta x, that's going to be 9 meters per second. So that's the positive in front. So now I'm just going to be solving for magnitudes. And the time is 1.63. seconds. So how far it's going to go, we figured it's going to be somewhere in between. It's not going to be at this far. It's going to be somewhere shorter than this, right? So it's going to be 9 meters per second. It's going to be 9 meters, but then 63% of another 9 meters. So let's get our calculator out. So 9.63 times, why did I do that? It's 9 times 1.63. Okay, there we go. So 14.67. So 14.67 meters. Okay. So basically, here's what you do. You kind of sketch out the motion of it and try to actually put the actual relative scale of things in here. And when you do that, by me putting that it's falling only 13 meters, but its initial velocity is 9 meters in 1 second, that means 9 meters is really far, right? Okay, in the first second, and it's only 9 meters up, right? And by me also attaching the acceleration vector to that 1 second mark, where it was at 1 second, right? 1 second right here. And this is 0 seconds, right? So at that 1 second mark, it will have dropped actually to right here. Okay, and now it's going to be dropping a little bit more. So really, it's moved that direction, right? So by me attaching the acceleration vector to here, it showed me that after that first second, it's going to be moving. It's going to have actually, let me get rid of this. After that first second, it's going to have fallen down from that 1 second to 2 second mark. It's going to have fallen down negative 1.9, negative 9.8 meters down over that next second. So that kind of helps us kind of gauge what is happening and see its displacement from those vectors. Okay. Well, let's go back to this. They do a similar problem in night. So there's a lot of different types of problems, but in all of these different types of problems, just really quick, find the time. Find the time in each one of these problems. The trick to doing all of these problems is finding the time that it takes to fall down or move to the right. Because that, if you take the time that takes to move to the right, that distance, well, that's the time it takes to fall down that distance, right? So time is the link between the y direction motion and the x direction motion. Okay? they do the same problem, different way. A stuntman is going to drive a car 20 meters per second off a 10-meter high cliff. So again, this is probably going to have maybe a time of flight. If you're falling at 9.8 meters per second squared, it's probably going to have maybe a delta t of maybe 1 second if you're lucky, right? So they're doing the same thing. They draw a pictorial representation. They then list out their knowns and unknowns, and then they start kind of estimating some things. And then they put together the equations of motion, right? The x direction equation of motion, y direction equation of motion, just like we just did. And so we could see that this is also just barely over 1 second, right? Just like we were guessing. And so they basically did the same process that we just did with that other problem. Okay? Okay, well, I hope you liked this video. And we're going to be moving on to the next type of problems where a ball is thrown into the air, and then caught at the same height. So now we're going to be working with problems where they do have an initial velocity in the x direction and an initial velocity in the y direction, but the heights are the same of where it lands compared to where it is caught. Okay, bye.